Okay, guys, section 6.3. In section 6.3, we're talking about exponential functions. So this is section 6.3, Introduction to Exponential Functions. So with exponential functions, okay, that's when the input it's in your exponent, in the exponent. So we have to review law of exponents. So let's review law of exponents. So I'm going over the most important properties. Couple things here. A, B are the base, and S, T letters will be exponents. Okay, so the first property which we need to know, it's a product property. You have B to the power of S times B to the power of T. What we're going to do when you have the same bases and multiplication, you're going to copy base once and add exponents. Okay, we call this product property. Just a quick example. Let's say you have 2 to the power of 2x times 2 to the power of x squared plus 7. So you can apply product property. The base it's 2. You copy base once when it's a multiplication and you're adding exponents. So that will become 2x plus x squared plus 7, which is the same as 2 to the power of x squared plus 2x plus 7. Okay. Second property, it's a power property. So you have base to the power of s, but also we're going to bring that expression to the power of t. So when you have power of power, you copy base once and you multiply exponents. Okay, we call this power property. And I will give you an example. Let's say you have 2 to the power of 3x, and then we're going to bring that to the power of 6. Okay, so our base is 2, copy base and multiply exponents. So that will be 3x times 6, which is the same as 2 to the power of 18x. That's how the power property works. The third one, it's a distribution property. So you have two expressions, a times b to the power of s. What we can do here, we can distribute power to each base. So that will be a to the power of s times b to the power of s. Okay, so here I apply distribution property. Let's say you have example x squared. I don't want to introduce that yet. Basic one. Let's say you have x times y to a second power. So you can rewrite that as x to a second power times y to a second power. That's how you apply distribution property. Next one would be quotient property, which means division. So we have b to the power of s divided by b to the power of t. So we have a quotient of two exponential expressions. They both have the same base, so you can rewrite that as b and you're going to subtract the exponents to the power of s minus t. We call that quotient property. So let me give you an example. Let's say you have 2 to the power of 3x over 2 to the power of x. So since we have a quotient of exponential expressions, both have the same base, which is 2, you copy base once and you subtract exponents. So that will be 3x minus x, which is the same as 2 to the power of 1x. Quotient, another important rule, rule 5, 1 bring to any exponent, it's always equal 1. Rule 6, 0 exponent. So any expression, any base to the power of 0, it's always equal 1. Example of this one, 2x squared y to the power of 0. Whatever you have, right here in the parenthesis, you see exponent 0, this is always equal 1. And here, let me give you exponent. 1 to the power of 3x will be 1. And reciprocal property, 7. Reciprocal property. Or you can know that as a negative exponent. So base bring to negative exponent. When you see negative exponent, you take the reciprocal of base and that exponent become positive. Okay, you can rewrite that also as 1 to the power of s over b to the power of s, which will give you 1 over b to the power of s, because 1 to any exponent is always equal 1. So example of negative exponents, 2x to power of negative 3. This is the same as 1 over 2x. And when you take the reciprocal of your base, in this case your base, it's 2x, and that exponent will become positive. And this is the same as 1 over 2x to the third power. And here we can simplify, so this is 1 over 2 to the third power times x to the third power, because I applied that distribution property. And this is the same as 1 over 8x cubed. So that's what happens when you see negative exponent. You take a reciprocal of the base. Okay, next. Let's talk about the definition. Now, when we review the rules of exponents, now we're going to talk about exponential function. So, definition of exponential function. So, exponential function is a function of the form f of x equals c times a to the power of x. Okay, so let's talk about it. C, okay, we call initial value. C, its initial value, which is technically your y-intercept. Y-intercepts, that means on the graph, you have a point 0, comma c. Y-intercept, x value has to be equal 0. Okay, what we know about C, the initial value, that C, it can not be 0. Next, A we call the base of exponential function. What we know about base, okay, so a couple restrictions about base. A has to be greater than 0, and A, the base can be equal 1. That's the information about base. And X, it's our input, okay, no restrictions about X. So also A, it's a base, but you're going to see that base, sometimes they're going to use the growth factor. Okay, that's the growth factor. What is important about exponential function? This is super important. That part will help you to find the base. Okay. In exponential function, the ratio of two consecutive outputs, which means f of x plus 1 over f of x, will always be equal to a, which is the growth factor, the base of exponential function. Okay, so how you read that? You read that this is the theorem, the ratio of consecutive outputs, which means y values, is always equal to a constant 8. Constant A, which is the base, which is the growth factor. Super important. Technically, this is how you're going to know that the given points, because you may not see the equation. Of course, you're going to know that you have exponential function when you're going to have a base bring to the power of x. Okay, so your x is going to be exponents. But sometimes they're going to give you the points, and without graphing, you will have to decide if this function is exponential. So this is your key. This is what you're going to use. The ratio of consecutive outputs in exponential functions all the time equal, and it's equal to constant a, which is the base. Okay, so I'm going to quickly prove that. So let me prove that. Okay, and I like to show students the proofs because again, if somebody will consider study math, there's a lot of stuff which you will need to prove it. So f of x, it's an exponential function, c times a to the power of x. And we want to prove that f of x plus 1 divided by f of x is equal a. So let me create f of x plus 1. So I'm going to replace x with x plus 1. So this is the same as c times a to the power of x plus 1. So now I'm trying to prove the left side of that theorem, that f of x plus 1 divided by f of x, and I'm trying to show you that this is equal to a, which is the base of exponent. So f of x plus 1 has a form as c times a to the power of x plus 1 divided by f of x, which is c times a to the power of x. You have multiplication, so you can cancel the initial value c, and we end up with a to the power of x plus 1 over a to the power of x. And now you can use the quotient rule. Since we have the same bases, copy base once and subtract exponents. So you have x plus 1 minus x. And x and negative x cancel. We end up with a to the power of 1, which is a. And we're done with the proof. So the proof is, everybody can do it in this class. Okay. Next, what we're going to talk about it. We're going to do the example. Okay, but before we do the example, I want to review. So this is the note that the ratio of two consecutive outputs always equal to a constant A. So this is how you're going to know if given function is exponential. So let's just catch up. Let's just write two important notes. For exponential functions, always, again, the ratio of two consecutive, okay, next to each other, next one, outputs is always the same. And equal to A, which is the exponential graph. Now, let's review what happened with linear function. How you're going to know that you have linear function. For linear function, that's going to be a difference. The average rate of change. Average rate of change, this is just slope. Okay, that's our M. Average rate of change is always the same. So let's review the slope formula. Y2 minus y1 over x2 minus x1. So this is the slope formula. Why I'm reviewing this one? Because that's going to be something what you will need to prove it. You will need to show in next example. So I'm going to solve number 27 from page 435. Okay, so let me see. Okay, do I have it? Yes. So this is page 435, and I want to prove it number 27. Okay, so in those problems, okay, in number 27 through 34, you have to determine whether the given function is linear, exponential, or neither. For those that are linear functions, find linear function that models the data. So if you will decide that your function is linear, you need to create the equation y is equal mx plus b. If for those which will be exponential, you have to find the equation of the exponential functions. For the one which are neither, we're not doing anything. We're just proving that it's neither. So this is number 27. I'm going to copy this down. Let me see if there's a way that I can copy. Hmm. No. Okay. I'm not so good yet with that. Okay. I was trying to insert what I copy. But you guys saw it. So let me just. No. Still learning. Okay. Okay. So 27, this is what they gave you. They gave you that table. just copy this one, x, f of x, they gave you points. -1 comma 3, 0 comma 6, 1 comma 12, 2 comma 18, and 3 comma 30. And they asking, okay, if this is if those points are points of linear function, exponential, or neither. Okay, so what I'm going to do first, let's check if f of x is exponential. So for exponential function, so for exponential function, I told you guys that the ratio of two consecutive outputs is always the same. So two consecutive outputs. So I'm going to create the ratio. I'm taking 6. I'm taking the ratio of two consecutive outputs. I'm putting f of x plus 1. So this is what I'm trying to show, that f of x plus 1 over f of x all the time is the same. So f of x plus 1, so I'm taking 6, and I'm dividing by the previous output, which is 3. And I'm getting 2. Then next I'm working with those two right here. So I'm taking 12, and I'm dividing by 6. I'm getting 2. So far, we good. But then I'm working with those two consecutive outputs. So I'm taking bigger divided by smaller, 18 divided by 12. And here, I can reduce both of them by 6. So I'm getting 3 over 2. So I can stop. They're not equal. Because if they will be exponential, all the time I will be getting 2. So because I got here 3 over 2, I know this is not exponential. Okay, also exponential functions, the y value should increase super fast. So we had huge, big increase at the beginning, but then we have 12, 18. Okay, so if it's not exponential, that's it, you're done. Now let's check if f of x is linear. So what you will need to do, you will need to find the slope between each pair of points and check if your slope is equal. So for linear function, I'm going to first work with those 2 points. Okay, so if you guys, you can rewrite that. You have first one, which is -1 comma 3, and the second one, which is 0 comma 6, and I'm going to find the slope using the formula y2 minus y1 over x2 minus x1, because each linear function has equal slope. Okay, so let's just label them. This is x1, y1, x2, y2. So I'm getting 6 minus 3 over 0 minus -1. I'm getting 3 divided by 1, which is 3. And next, what I'm going to do, I'm going to find the slope between those 2 points, 0, 6, 1, comma 12. So 0, 6, just put in different color, 0, 6, 1, comma 12. So this is my x1, this is y1, this is my x2, y2. So I'm finding the slope using slope formula. y2 minus y1, so we have 12 minus 6 over x2 minus y1, x2 minus x1, which is 1 minus 0. So we're getting 6 divided by 1, which is 6. And I'm going to stop because they already, like you see, those slopes are not the same. So there's no point for you to keep checking slope. Okay, since just put since slopes are Not the same. This function is not linear. So, not linear, not exponential, the answer of this problem will be neither. And I want to do one extra problem just to show you what to do and find how to find the equation of something what either will be exponential or linear. So I want to talk about page 435, number 31. So this is number 31, page 435. So going back, like you guys see, there's in your textbook many problems which they asking you for the same thing. I want to talk about 31. Okay, so this is what is given. They give you points, x and y. You have to decide if this is linear or if this is exponential, or none of them. So in 31, they give you one, two, three, four, five, 6 points. -1, 3/2, 0, 3, 1, 6, 2, 12, 3, 24. Okay, exponential and linear. Let's see. I'm going to prove it. So let's check if f of x is exponential. So for exponential functions, this is what you're proving, that f of x plus 1 over f of x all the time, it's the same, and that should be equal to the base of exponential function, exponential graph. So we're taking the ratio of two consecutive outputs. So right now what I'm doing, I'm taking the ratio of two consecutive outputs. Okay, so I have 3 divided by 3/2. So number divided by fraction means this number is multiplied by reciprocal of 3/2, which is 3 times 2/3. And we're getting 2. And now I have to continue. Okay, now I'm going to take the ratio of two next consecutive outputs. So now I'm checking what is the ratio of 6 and 3. So 6 divided by 3, I'm getting 2. So far, we good. Okay, of course, you have to show it for all of them. So next, what I'm doing, I'm checking the ratio between next two consecutive outputs, which is 12 divided by 6. We're getting 2 again. And one more time, check the ratio between the last two consecutive outputs, which will be 24 divided by 12. We're getting 2. So yes, they are the same. Okay, so all the time we're getting a. That means this function is exponential. So I know that the base of our exponential function is equal to. So yes, exponential. And that ratio of two consecutive outputs give you the base. Okay, base is equal to, which we call exponential growth, exponential factor. So let's build, since this is exponential, next create the exponential model. The exponential model is f of x, it's equals c times a to the power of x. So at this moment, we know a. We know a is equal to. By finding the ratio of two consecutive outputs, you're always going to get the base. Okay, last thing, what you need to figure out is c. Don't forget that c it's the initial value, which means y-intercept. So let me check right here. Look what happened. In that table, they gave you y-intercept. They gave you 0.0, comma 3, okay? Which means this is the y-intercept, which is c. c is equal to 3 from the graph. I didn't do anything. This is from the table. So our exponential model will be f of x, it's equal 3 times 2 to the power of x. This is our exponential function. Okay, next what we're going to talk about, and again, if you will get, for example, linear function, so you will have to create the equation y is equal mx plus b. Okay, m will be given because you will find the slope, and you will have to find the y-intercept, most likely will be given also from the table. Okay, next super important topic, graphs of exponential functions. So there is two graphs, two cases of exponential functions. The first one will be increasing. So I will say the first case, increasing. That's the one which by now I think everybody knows how exponential function graph looks like because of the coronavirus, which I really don't want to bring it and keep anybody depressed, but that's what we see. Okay, so this is exponential function. Okay, that's how the graph looks like. It's increasing graph. Okay, we have increasing and we have decreasing. So exponentially increase. Okay, so f of x equals c times a to the power of x. And I'm going to talk about increasing graph first. How are you going to know that your graph is going to be increased? The base exponential factor is going to be greater than 1. An example of increasing exponential function is y equal 2 to the power of x, which you always can put as 1 times 2 to the power of x. So you see exactly that c is equal 1 and the base is equal a. And like you see, a is greater than 1, so this graph will be increasing. Okay. What is important, and I recommend it to memorize that, you always have 3 major points. Just memorize them. Okay. 0, comma c, which is the y-intercept. 1, comma a, and negative 1, comma 1 over a. We always graphing with those 3 points. Okay. So based on our example, okay, right here, going back to this example, if I will have to graph it, so again, c is equal 1, a is equal 2, knowing those 3 major points, so 0, comma c, so I already know that we have a point 0, comma 1, since c is equal 1. That's the coefficient in front of the base. 1, comma a, look into the equation, so it will be 1, comma 2. And the last one, it's negative 1, comma 1 over a, which is negative 1, 1 half. And you quickly have 3 points, and you can sketch the graph. So this is how the increasing function looks like. at the beginning, increase slow, and then it's fast increase right after crossing that y-intercept. Okay, so this is that point 0 comma c. Okay, so let's describe. Okay, so let's talk about the domain. Okay, domain. Domain, that's your x values. So it's going to be from negative infinity to infinity. Let's talk about range. Range, that's your y values, which will be from 0 to positive infinity. What you guys have to be careful here in this graph, that your function will never touch y equals 0. So y equals 0, the graph is when x approaching, when x approaching negative infinity, okay, getting closer to negative infinity, y values approaching 0 but will never touch. So that y equals 0 we call horizontal asymptote. So each exponential graph has a horizontal asymptote. Okay, how you're going to find it? When x is getting smaller, the y values will be approaching the given value. It's not all the time y equals 0 because we may have transformation. Okay, so the main range, of course, our function is increasing because a is greater than 1. Our exponential factor is greater than 1. No x-intercepts. Y-intercept, 0 comma c, it's the y-intercept. Function is increasing. And I think that's it, what you guys need to know, okay? Don't forget that you're always graphing exponential function with those 3 points, 0 comma c, 1 comma a, negative 1 comma 1 over a. Next, the second graph. Let's see how, okay. The second graph, it's going to be a case of decreasing graph. So exponential functions, they also can be decreasing. So this is decreasing case. So you have exponential graph y, it's equal a, let's put it this one, c times a to the power of x. How you going to know it's decreasing? The base, it's greater than 0, but it's less than 1. Okay. And let me just show you the example. Example of decreasing function can be y, it's equal 1 times 1/2 x. Okay, so like you see, this is your base, and base it's less than 1. However, it's greater than 0. Couple things, okay? You guys be careful. I know you can catch that, but sometimes they can give you something like this. Okay, so let me put a star. Y it's equal 2 to the power of negative x. Okay, so this graph is also decreasing because look what happened. You have that negative exponents. By now you know that when you see negative exponents, this is the same as 1 over 2 to the power of x. And then you will know that the base is less than 1, so it has to be decreasing. Okay, in our textbook, I see many examples like this. Okay, they they put it that way. Okay, make sure that you know that this is the same as 1/2 to the power of x. Okay, so C initial value, A it's, oops, let me just write this down again. C, it's your initial value, which means the y-intercept, 0, comma C. A, it's the base, which they're going to call growth factor. Okay, for decreasing case, A is greater than 0, but less than 1. That's for decreasing. And you're still graphing the same way. You're still graphing with 3 major points. So that still applies 0, comma C, 1, comma A, negative 1, comma 1 over A. And let's just use our example. Y is equal 1 times 1/2 to the power of x. So 0, comma C, you will have 0.0, comma 1. 1, comma A, you will have 1, comma 1/2. And negative 1 over A, so that will be 1 divided by 1/2. So this is the same as negative 1, comma 2. Okay, so how the graph looks like, it decreases exponentially. Okay, so it looked like this. So after the graph, after crossing the y-intercepts, okay, decrease at the beginning very fast, but after crossing y-intercept, it's slowing down. Okay, and that's the 3 major points which I mentioned. This is your 0, comma C. This one will be negative 1 over A. And this point here will be 1, comma A. Okay. So decreasing, the rest is the same. Domain is the same, the horizontal asymptote is the same, and range is the same. So again, don't forget that y equals 0 is the horizontal asymptote. So your exponential graph can be increasing or decreasing. Okay. Okay. Next one. Let's talk a little bit about graphing. So let me go over. This is number 43 from page 435. 435, 43. Okay. Cannot go more. Should be. Okay. Doesn't go more. Okay, but technically what they want you to do, they want you graph exponential function using transformation. Okay, so we have f of x equal 2 to the power of x plus 1. Okay, and they want you to use the transformation. So how are you going to do it? The parent function which is your original function, will be y is equal to the power of x. So you should graph parent function first and then recognize that you have that plus 1, which means you have vertical shift 1 units up. So you will move everything 1 unit up. So let's graph y equal to the power of x first. So this is the same as y equal 1 times 2 to the power of x. C is equal 1, a is equal 2. To graph this one, I'm using the information which I gave you. Always graph with 3 major points. 0, C, that will be 0, comma 1. 1, comma A, in our case it's 1, comma 2. And then negative 1 over, comma 1 over A, in our case it's negative 1 and 1/2. So you will graph this basic exponential graph. 0, comma 1. Then you have 1, comma 2. And negative 1, 1/2. And now our transformation, which is f of x, it's equal 2 to the power of x plus 1. So what we're doing, we're shifting this graph 1 unit up. So you're taking each point and you're moving 1 unit up. So this point will be here. This point you're bringing 1 unit up. So it will be 1, comma 3. And this point, which was negative 1, comma 1/2, we're bringing 1 unit up, so that will be negative 1 and 1.5. Okay. So it's same shape, but we just bring entire graph 1 unit up. Okay, so those points, again, I just show you 0, comma 1 will become 0, comma 2. You're just adding 1 to the y coordinate. 1 and 2 will become 1, comma 3, and negative 1, 1/2 will become negative 1 and 1/2. We're just adding 1 to y value. Okay, so you may see some graphs of transformations. What I want you to notice that originally this graph y is equal to the power of x had the horizontal asymptote y equals 0. Okay, so this graph y equals 0 is the horizontal asymptote of y equal 2 to the power of x. Now, check what's happening. We graph y is equal to the power of x plus 1. So now, y equal 1, our vertical shift unit is the horizontal asymptote. Okay, so my graph, it's done by hand, but y equal 1, it's right here. Like you see, my graph should, when x approaching negative infinity, my graph should be getting closer to y equal 1, but should not intersect. So that's the new horizontal asymptote. Okay, I'm going to stop this one and I will record one more video for you guys.